In this podcast, we are going to go over positron emission as well as the medical applications of positron emission. You may start to notice as we talk about positron emission that it is very similar to beta emission. Because it is so similar to beta emission, students will often confuse these two types of emissions. So be very careful as you're working problems that you're kind of keeping that in the back of your mind. Our terrible definition for positron emission is the decay of a nucleus by emitting a positron. Dumb, I know. We are going to use a Greek symbol that is shockingly similar to the beta particle, and we are going to use the Greek symbol beta with a plus sign. Or what I prefer to use is an electron with a +1 charge. So we have a positively charged electron here. No mass. That mathematically is more helpful to me when I'm trying to do a reckoning of where my neutrons and protons have gone, where and how they've changed. So because we're talking about electrons, we do consider them to have negligible mass. That doesn't mean they have no mass, it just means that compared to protons and neutrons, they're much, much, much smaller. And it does have a positive charge. So many of the properties of positrons are similar to beta particles, so therefore the damaging and penetrating powers are both considered moderate, just like beta particles. When talking about PPE for positron emitters, it's very similar again to our beta emitters. So you could put a wall between you and the positron emitter and it would not be able to penetrate that wall. They can travel a bit further than your alpha particles. They can pass through paper, which is different than alpha particles. And they can pass through 4 to 5 millimeters of skin. So again, just like beta particles, heavy clothing, lab coats, and gloves are recommended when you're around positron emitters. All right, let's talk about the general reaction. In a positron emission, we are decaying a proton in the original nucleus into a positron, that's the beta with plus sign, as well as a neutron. So big takeaway here, a positron is decaying into a neutron. So we know that we're going to lose a proton, so our atomic number is going to go down by 1 and our mass number is going to go down by 1. But because the proton is decaying into a neutron, the mass number is going to go back up again. So what this looks like is that we have no change in our mass number, but we have a decrease by 1 in our atomic numbers. So if you have your cheat sheet handy, go ahead and pause the video and make sure that you're adding this to it. We will talk about this in a couple slides in a little bit more detail, but I just kind of wanted to get this floating around in your head. We start with an unstable parent nucleus. So this is our radioisotope, our positron emitter. And what happens is your proton decays to a neutron. When the proton decays to a neutron in the nucleus, a neutrino is emitted. We're not really worried about the neutrino. That's not a conversation we need to have, what goes on there. But what we are concerned with is that you emit that positron. Notice that it is a symbol of an E with a positive charge. What happens to that positron next is kind of exciting because of a positron and an electron, those are two oppositely charged particles. If those combine or come in contact with each other, there's an annihilation event where both particles are destroyed. That's not the cool part. The cool part is when annihilation occurs, we're going to release photons of light, which we can use medically. All right, it's time for an example. So here we have carbon 11, and we see it is emitting a positron. We know it's a positron because we have the symbol of an electron, but it has a positive charge. If it were a negative charge, we'd be talking about beta emission. And we see that there's a decrease in the atomic number, which we expect because we have a proton decaying into a neutron, so there should be a decrease there. Notice that our mass does not change, but let's go ahead and draw our line in the sand between reactants and products and just take an accounting for everything that's happened. So we have 6 protons in carbon, and in the products we only have 5 protons. Well, that makes sense because a positron emission is a decrease in proton number by 1. Our positron is really easy to count because it has no mass, has no neutrons, no protons, so this gets real easy going down. We got straight goose eggs. All right, neutrons, 11 minus 6 is 5, so we have 5 neutrons for a mass of carbon of 11 and a total mass on the reactant side of 11 as well. Looking over at our product side, 11 minus 5 is 6. This also gives boron a mass that is equal to the total mass of the reactant side. So we've accounted for both sides for the protons and neutrons. All right, we're going to go into the general functionings of positron emission tomography. So we start, as we talked about a couple slides ago, with this image where you have your unstable nucleus that decays to a more stable nucleus. In the process, a proton decays to a neutron, and we emit both a neutrino. Don't care. Don't tell the physicists I said that. We don't care. What we do care about is that positron that's emitted, because it can go through an annihilation event. So if a positron and electron combine, annihilation occurs, destroying both particles, but it releases a photon of light, and that photon of light is critical for a PET scan. Okay, so before we get into the PET scan, we are going to need a positron emitter. So there's a couple ways we can do this. You're going to take a positron emitting isotope and you're going to add it to a chemical molecule. Glucose is usually used, and in this case we're seeing glucose being used. So we can use an isotope of fluorine. There's isotopes of carbon that we can use. This image in your bottom left-hand corner is showing a radioisotope of fluorine being used. Doesn't matter which one you're using as long as it's a positron emitter and it's safe to be administered to your patient. So we take our glucose molecule and our positron emitting isotope, we chemically combine those, and now we have a PET tracer. That tracer can be injected into our patient. Once it's injected, we have an unstable nucleus trying to form a more stable one. So we have those positrons being emitted. Well, this tube is your PET detector ring. So you're inside this tube, and as you're emitting those positrons, or as your tracer, your nucleus is emitting those positrons, there's going to be annihilation events. Your positrons are going to combine with electrons, causing an annihilation event, which is releasing that photon. And this PET detector ring is detecting that light that's being emitted. We then use computer software to process that image, to analyze the data, and we wind up with a nice picture of your insides. But this all depends on positron emission. This all is a result of an unstable nucleus decaying to become a more stable one. All right, so I like looking at these images side by side. Here we have a CT scan of a patient, and here we have a PET scan of the same patient. And notice these blue areas that are lit up. So the PET scan has a little bit of an advantage when looking at cancer over the CT scan. So here, the blue represents cancer. And it's showing to our medical providers that the cancer has spread to the lymph nodes. Because the cancer has spread, this is going to change the diagnosis of the patient from stage 1 to stage 3. It's also going to change what treatment options are available. So surgery is not going to be the best treatment option at this point since it has spread. We wouldn't know that unless we had a better scan than a CT scan, such as a PET scan, which highlights that cancer. The bottom images, we are seeing the same patient. Again, we have a CT scan versus a PET scan, and it's again showing malignancies in the lymph nodes. It's also showing that brighter spots, your cancer. It allows for the doctor to visualize the cancer versus other structures that are normal associated with blood vessels. So it gives just a little bit better idea, a little more clear image of where the cancer is. Okay, so if you're feeling confident, feel free to pause this, work the problem on your own, check back in with me later. But I'm going to walk you through how to do some practice problems. You're going to write the balanced nuclear equation when xenon 118 decays by positron emission. All right, so looking at our periodic table, xenon is atomic number 54, And in positron emission, we are going to emit a positron, or a positively charged electron. And I know that one of my protons is going to decay to a neutron, which is why my atomic number decreases by 1. So 54 minus 1 is 53. Looking at the periodic table, that is iodine. And my mass number does not change, it stays the same. So this is my balanced nuclear equation for the positron emission of xenon-118. Here's another type of question that you might see. This stretches the brain muscles just a little bit here, and they're asking us to complete the balanced nuclear equation, but instead of giving us the positron emitter, we have to work our way backwards from the product, but we can do this. So right away I notice that we have a positron emission, because we have a positively charged electron. So I know that this value is Z minus 1. So if I add 1 back to that, my original species had 37 protons because my new species is Z minus 1, 37 minus 1, or 36. Looking at the periodic table, that is rubidium, and our mass number does not change. So it should be rubidium 77 for our missing particle.